The past isn't fixed. How quantum mechanics challenges our understanding of reality for centuries, we've operated under the assumption that the past is concrete. Adolf Hitler either died in 1945 or he didn't. But quantum mechanics, the most successful scientific theory ever devised, suggests this isn't necessarily true. At the smallest scales of existence, reality isn't predetermined, and this fuzziness extends to our perception of what already happened. The quantum world. Uncertainty at the core, the problem isn't that quantum mechanics is wrong. It's that it's profoundly counterintuitive. Unlike the macroscopic world, where objects have definite properties, the quantum realm operates on probabilities and uncertainties. An electron fired at a barrier might bounce back or tunnel through. An atom might decay or remain excited. And we can only predict the likelihood of either outcome, not the outcome itself. This uncertainty isn't limited to the future. Quantum mechanics implies that the past isn't a fixed record, but a collection of possibilities until observed. Think of history as a superposition of alternative realities, dissolving into blurriness until measurement forces one version into existence. How measurement shapes reality. When we observe a quantum system, we don't simply reveal an existing reality, we create it. Imagine countless ghost electrons existing in multiple states until a measurement collapses them into a single, concrete location. This isn't passive observation, it's active participation in shaping reality. The key is the experimenter's choice. Measuring for position forces the electron to behave as a particle. Measuring for speed forces it to behave as a wave. The electron isn't inherently one or the other, it becomes one based on how we choose to look at it. Retrocausation, the past determined by the present. The truly bizarre implication is that this choice isn't just about the future, it retroactively affects the past. The nature of the electron wave or particle before the measurement is determined by the measurement itself. It's as if our present actions reach back in time and shape what was. This isn't time travel in the traditional sense, but it suggests that the past isn't a pre-existing, immutable record. Instead, it exists as a superposition of possibilities until the present moment collapses it into a single history. Physicist John Wheeler put it succinctly: "The past has no existence except as it is recorded in the present." The delayed choice experiment, this idea isn't just theoretical. The delayed choice experiment, first conceived by Wheeler, proves it. In this setup, the decision of whether to observe which slit a photon passes through can be made after the photon has already passed through the slits. The results confirm that the photon's behavior, wave or particle, is determined by this delayed choice, effectively changing the nature of its past trajectory. The experiment doesn't change what happened, but it illustrates that in the absence of observation, multiple pasts coexist. The act of measurement doesn't select a pre-existing history. It reduces the number of contenders, solidifying one version into reality. Implications for our understanding of time. This challenges our fundamental understanding of time. Einstein believed the past, present, and future were illusions, but quantum mechanics goes further. The past itself is malleable, dependent on the present. The macroscopic world gives us the illusion of a fixed history, but at the quantum level, it dissolves into a blurry amalgamation of possibilities. The universe isn't passively unfolding. It's actively being created through observation. The past isn't a destination we've arrived at. It's a landscape shaped by our present choices. This is not just a scientific curiosity. It's a fundamental shift in how we understand the very fabric of reality.